reduction into active polar fluids. And we ended last time with in a state of confusion. I'm trying to resolve this confusion in a second. But first, let me remind you what we did so far. So after giving you a few examples, we're starting to develop the general theory, and we are going to use standard linear thermodynamics for this, non-equilibrium thermodynamics. And so what we did first, we identified hydrodynamic modes by looking at conservation laws. So we have mass conservation, which I've written down now in absence of any terms that give you polymerization, depolarization. You can write alternatively also this in terms of particle density, number density, and we simply have the relation that O equals m times n, where m is a molecular mass. Right? we then have momentum conservation. So G was the linear momentum, usual one, sigma the total momentum flux density or stress, and I've written it down here in absence of any external forces, because this is the case we are going to look at later. And then we also looked at the density of angular momentum, and the corresponding equation is given here. For the components of the total angular momentum flux density, we can split it into two parts. One is due to simply the stresses that we have in the system, and the other part is due to molecular anisotropies. Right? So this is reflecting that we have polar order in our system. Now, what we then went on was to determine the antisymmetric part of the total stress, and this is the way that I want to keep it. So I told you that there are always different ways of writing down the stress tensors, because you can gauge it if you want. You can always basically make this one completely symmetric, but I want to keep this antisymmetric part, and in the way we've written it down, I identified the antisymmetric part to be given basically by the gradients of the angular momentum flux density tensor, which is due to the molecular anisotropies. And then we went on to look at static situation, hydrostatics, and wrote down the variation of the energy. And this is now basically only done in order to get some useful relations that we are going to use later when we're going to talk about non-equilibrium. Now, until here, and also for further down what I'm going to do, if you are very familiar with pneumatic liquid crystals, then there's nothing new in here, right? I mean, this is all standard. These are calculations that have been done basically more than 50 years ago by Ericsson, and there's no, and basically he presented them already in a very similar form, so there's nothing too new. Okay, so but now let's look at a few variations that we can do and see what we can get out of that. So the first variation that I wanted to look at was at a pure rotation of the polarization vector only. So we have said that delta P alpha is something like sun alpha beta gamma, and then we had a delta theta and P gamma. And we applied this one, as we did already last time, and from that followed an expression for m alpha beta gamma, which I do not bother to repeat here. And then the point came where I unfortunately confused you, and this was when I said, now let's look at a case where we look at displacement. And in this case of displacements, I wrote down the variation in the density in the following way. I said, so this is U gamma G gamma n. So here already I forgot to tell you that what I'm looking at, what I'm interested in, are only displacements that keep my density conserved, so it's incompressible if you want. So I have the condition divergence of U should be 0. Okay. That's the variation. So everything I'm doing now is basically restricted to incompressible systems. And the second thing I did, and this is then where really the confusion started, was when I said, okay, now let's also write down the variation for the polarization for the order parameter, and I also wrote it down in this form. And then the comment came, which is of course true, that if you, let's say you have an elastic sheet, you add little arrows to it, and now you deform this sheet, then the arrows will also deform. And this is not represented by this variation. That's true, it's not. But first of all, I'm allowed to do basically any variation I want to do, right? I mean, this is the general expression, and here already I restricted myself to a variation where I do just vary the polarization, the order parameter, but nothing else. And here now I'm doing another kind of variation where again I separate two the degrees of freedom, namely the spatial degrees of freedom, if you want, from the order parameter degrees of freedom. And from this we will be able to determine a certain quantity. And now the question is if this quantity is helpful. Does it tell us anything useful? And well, this quantity that we are going to get out is what people call the Ericsson stress, and has been proven useful in at least thematic liquid crystals. If it is a useful quantity for active gels that I'm going to consider, it remains to be seen, but here we are still at the equilibrium case, hydrostatics, nothing wrong with that. So what I propose is that we continue with this. So we have basically now separated variations, pure variations in the polarization vector from pure displacements. We are going to identify a certain number of quantities. With these I'm going to continue to develop the theory, and in the end we then get our dynamic equations. I can already announce here, and I will make this remark later probably again, that obviously again the choices of the stresses and so on, they are not unique. What should be unique is the physics that comes out in the end, right? And this calculation I've not yet finished, so I'm not able to tell you anything about this. So we are going to stay with the definitions that I'm going to derive now. Any remarks or questions on this point now? Okay, so if this is not the case, then
the third equation, the first term shall be the tensor shall be L instead of.
Oh yes, I'm sorry. Thank you very much. This is how we noted the angular momentum density. Okay, now let's plug this everything that we have written down here into the equation for Bob. So first have a mu minus u gamma d gamma n. Then we have our df naught dp alpha, and now u gamma d gamma p alpha. So I have to take the next term, which is the df naught d beta p alpha times d beta of u gamma d gamma p alpha, and that's that for that. And then we have the surface term, which I just keep the way it is. Okay, now what can we do? Well, first of all, I'd like to do some partial integrations. So let's do it first on the first term. So we continue like this. So we have a minus d gamma, and then we have mu u gamma n. Then there's some term missing, so this can be written in the following form. This will be an n u gamma d gamma mu, and here I've used already that d gamma u gamma is 0, right? So this is this incompressibility condition that I've used here. Then I have a term that I want to keep the way it is, just like about this, and then alpha. then here I also want to do a partial integration, so I have on one hand the term df naught alpha q gamma d gamma p alpha applies to all that, and finally I have my d beta naught alpha times u gamma d gamma p alpha. And then again I have to add my surface term like this. Okay, so now what I do see is that I can group some terms together. So first of all, let's look at all the surface terms. So let's write it in the way that I change the index from gamma to beta, the first one. So this gives me an f naught. I have another surface term that is this one here. Keep in mind that I have to use the u gamma somewhere. And then this d beta gamma. And there's another one, this is this one here, which gives me minus df naught d beta p alpha, and then I have a d gamma p alpha, and all of this to factorize u gamma. So this is a flux through the surface, and then I have to add finally the volume terms. And so I have n u gamma d gamma u. That's one term. And then I have these two terms. They also have the same u gamma in here, and they have a d gamma p alpha, and the term in front of that is nothing but h. So this is plus h alpha, or molecular field, times u gamma times d gamma p alpha. And if you want, you can even factorize u gamma in this way. Okay. So this is what we obtain, and so now this is, as I said, my momentum flux to the surface. So I will identify this as a stress tensor, and this will be my Ericsson stress in the components beta gamma. So just let it write down here. And alpha beta, this will be nothing but f naught minus mu n alpha beta minus df naught d d alpha p gamma d beta gamma. Right? So this is the term that I wanted to write down, and this is what people call the Ericsson stress. So now the second thing that I can do here is I can assume that I have a constant displacement. So let's assume that now the displacement field is constant. So what I then do, I just translate my system without any further ado, and this implies that the free energy, since my system is in total translational invariant, should not vary. So from this, what we get is that delta f naught is equal to 0. So this gives me another condition, because now I can use the divergence theorem again to transform this one into a volume integral, and then the integrants have to be 0, and what I get from this is basically that the that d gamma sigma beta gamma Ericsson must be equal to minus n times d beta mu minus h, say gamma, d beta d gamma. Right. So this is a relation between these intensive quantities, and this is what we call the Gibbs-Duhem relation. I hope that I got the signs and the indices all right. At least I have the same indices on both sides. So that should be fine. Good. So that's a relation that we're going to use later. And now there's a third, or fourth, depending on how you want to count, a kind of variation that I would like to do, and that is a rotation of the whole system. And so in this case, what do I have to use? I have to use that U alpha is something like an alpha beta, gamma theta beta of whatever the axis is, so it's R gamma. So R gamma is just the components of my space vector. Let's say, so theta beta should be constant as a function of space, but just make really a global rotation. And then now I write down the variation of P alpha, and this is now minus U alpha, gamma P alpha, and then I have to rotate also the vectors themselves. So I have an epsilon alpha beta gamma theta beta P gamma. Right, so this is really a block rotation of my whole system. Again, since my system is invariant under rotations, we have that the free energy does not vary, and this gives me a condition on the antisymmetric part. This is something that I'm not going to show you now explicitly because this would take too long. So this gives me the antisymmetric part of the Ericsson stress, and this is given by 1/2 times H alpha P beta minus H beta P alpha plus 1/2 of D gamma M alpha beta gamma. And that again, so this is a relation that I'm also going to use in the following. I hope I have put in the right signs, but I think so, yes. So this is all for hydrostatics. So again, what I did basically I used some special variations in order to identify a few quantities, in particular the Ericsson stress, which is to some extent an analog of the hydrostatic pressure that we know from apolar fluids, and we determine in this way antisymmetric components of the Ericsson stress, and very importantly here the relation between the intensive quantities, the Gibbs-Duhem relation. Okay. And now the next step I want to make is to use linear non-equilibrium thermodynamics in order to get the equation of motions for these quantities that we set back. So yes, I mean we still have to determine equations, constitutive relations for sigma. We're not going to worry about m so much. You see why. And we have to also get an equation for the changes in time of the polarization vector. So I don't know, notation was like this. So constitutive relations, right? And for this, what I will consider is, as usual, the entropy production in the system. It's call it S dot. And as I said before, I'm going to constrain myself to a system where temperature is constant. So this is just a constant factor. And this is just equal then to the change in free energy in my system, unless I have work that is externally done on my system, which I'm going to neglect, or if I have any other flux of free energy through the system, then I would have to add it in here. But this I'm going to assume to vanish. So the only thing that I really have to look at is now the rate of free energy change in my system. And anticipating what I will find that I can write this as a sort of sum of generalized thermodynamic forces and fluxes. And so I'm using basically this expression only to identify appropriate pairs of conjugate forces and fluxes. And then in the end what I'm going to do is I'm going to expand all these fluxes in terms of the forces up to linear order. And this will then give me the desired constitutive relations I'm looking for. Okay, so this will require once again a little bit of calculations, not too many though. So what is now the free energy that I'm writing down here? So again I have to integrate over volume. So I will use the internal free energy that we are using so far. So it depends on the density, the number density in my system. Then I have the polarization vector. I have possibly gradients in my polarization vector. So this was the free energy that we had written down for the volume elements. But the volume elements themselves, they may be moving. So I have to also write down that they might have some kinetic energy. So let's write it in the form V alpha. Let's write it in the form G alpha divided by 2 rho. So this would be the kinetic energy part. And then comes a part which I call, let's say, F ATP. So this is basically everything that that takes into account of all the contributions that are coming from my fuel molecules, ATP, ADP, VI, right, which are driving my system in the end. And I will assume that I can really write them separately in this way. Don't have to, but let's do it. And well, this is now what I have to compute. So let's start with it. So we first have a dF naught by dN, which is just my mu, dTn. Then I have dF naught by dP alpha, dTp alpha. I have dF naught by d beta p alpha, dt d beta p alpha. This is this one, that one. Then we have to evaluate this one here. So this gives me a, I'm first deriving the numerator. So this gives me G alpha by rho is just V alpha. Then because I have a squared here, this goes away with the 2 times dt G alpha. And then I have a minus V alpha squared divided by 2 times dt rho. And now I finally have to do something with this term here. And here I will be very bold. I will not consider this term in detail, but I just anticipate what I'm going to see. Well, what will I have? I will have, first of all, diffusion. Diffusion will just distribute my molecules, and I will have reactions. So the reaction is basically the hydrolysis of ATP. So ATP will be transformed into ADP PI. And the sign of this reaction will depend on the difference of chemical potentials of these three species. So if I neglect spatial aspects, if I neglect the transport of the molecules, which at least for cells is a good assumption. The ATP is diffusing quite fast on the scales of all the processes that are of interest, and also it's produced at many places, so it's really nicely homogeneous. Then I can write down this time derivative basically in a simple form like R delta mu. So here I have already used basically this form. The generalized thermodynamic force would be the difference in chemical potential of ATP, ADP, and PI, so delta mu, and the thermodynamic flux would be just the rate of reaction. Right? And corresponding to this, of course, we still have the continuity equations for the molecular species ATP, ADP, and PI, but I'm not going to write them down explicitly because, as I said last time already, what I will assume basically is that the difference in chemical potential is fixed throughout the system, so in space but also in time. So there are some biological processes that maintain this, or there's some experimenter who is controlling this level. So I will use this rather as a parameter than as a dynamic variable, and therefore I do not consider the dynamic equations for these densities explicitly. Okay, so basically now you see always these couples, but we can do a little bit better and write them in a nicer form, and this is what I'm trying to do now. So first of all, we use the conservation law to replace dTn by what we have up there. So that's a minus mu d alpha n v alpha. Right, that's the first one. Here there's not too much to do. We'll keep this term times the partial derivative of p with respect to time. I will use the next term. Here I will do a partial integration so that I get the d beta on this term, and then you see reappearing our molecular field, so I can write this down in this way, the whole expression. The surface terms I do not consider, just wipe them under the carpet. Then we have to look at this term, so this is plus v alpha, and then here we have to use conservation equation for momentum, so this is a d beta sigma total alpha beta, and then again minus 1/2 v alpha squared dt rho now, and so I have to use again plus d alpha, let's call this beta, d beta rho plus r delta mu. So maybe we keep this for some time. This is now only algebra, there's nothing deep. So this one here I will also use a partial integration because I want to single out terms that are corresponding to my v in the end. So what I get from that is that I have an n v alpha d alpha mu, and we have, let's continue first with this term here, a plus v alpha d beta sigma alpha beta total, and then we have this term here. I will use a partial integration right now, so I will have a minus v alpha v beta times rho times d beta v alpha. Then I have the term that I did not yet write down, namely my h alpha dtp alpha, and I have my r delta mu. So this is already not too bad, but here I always will have this gradient in v, so it's also good to did I do there? Well, there I did something which I should not have done even. Just want to keep it in the way it is. u d alpha n. Do I want to keep this in this way? I don't remember. So we'll see this in a second. No, that was correct. Sorry for that. Alpha d. Where is the n coming from? Oh, that's correct. Alpha u. Okay. So now I'm going to use again partial integration with respect to this one here. And what I want to do here is I would like to use the Gibbs-Dewey relation that I've written down upstairs there. So this can be written as a V alpha. Now we have the n d alpha mu. N d alpha mu I can write as a minus d beta sigma Ericsson alpha beta plus h beta d beta d alpha p beta. Right. Yeah. So this is how I replace the n d alpha mu, and I write down here my sigma alpha beta total times d alpha d beta v alpha. I have another d beta v alpha coming from this term here, plus h alpha dt p alpha plus r delta mu. Doesn't really matter if you cannot read it. This is the term that we just have to keep track of. Okay, now we are almost there where I wanted to get to. So here we will do another partial integration. So then what we get is again a gradient of V alpha. So I can factorize this. So what I will write down is the minus times sigma total alpha beta. Then here I get a plus, so I have to use another minus. E. So this is this term and that term. Then I have a plus rho V alpha V beta times d beta V alpha. This is this term. And then I can, did I do it correctly? Oh yes, so then I still have this term here, which is a plus V alpha H beta, well, what does it say? V alpha D alpha P beta, right? I've just changed the order of these two factors. And since I have here a P alpha, I will just rename the indices, okay? So let's call this alpha, beta, beta, P alpha. And then I have a plus H alpha dt P alpha plus R delta mu. Okay? So basically this is the result that I wanted to get. Now I have really products of two factors each. So here's a flux or stress. Here's the conjugate flux or stress. And here I also have it almost seen there. I have the H alpha, and then everything else will be the temporal derivative of P. But we will still do some modifications. So first of all, what I would like to do now is I would like to neglect this term here. And this is because in the rest I will be just interested in low Reynolds number situations. Right? If you want, you can keep it. But we don't consider this in the following, so I can leave it out already here. Then I have the sigma tot minus sigma e And this I will call the deviatory stress. Because this is what deviates from the hydrostatic, from the Ericsson stress. And here I can do a separation into its symmetric part and into its antisymmetric part. So what I will call sigma alpha beta will be the symmetric part of the deviatory stress. So this is just given by sigma total alpha beta minus sigma alpha beta E minus, and now the antisymmetric part of the two stresses. And now it comes in handy that we have determined these parts already. The antisymmetric part of the total stress is just upstairs there. So so this is again the symmetric part. Well, let's just write down the expression for the antisymmetric part. So this is nothing but 1/2 d gamma m alpha beta gamma. And now the antisymmetric part of the Ericsson stress, this is the calculation that I've not done explicitly, but it's up there. So this is minus 1/2 h alpha p beta minus h beta p alpha. And then here's a plus, so it's another minus 1/2 d gamma m alpha beta gamma. And now magic happens, and that is that these two terms cancel, and the antisymmetric part is given only by this term. Well, that's nice. Why is this nice? Well, you will see why it's nice in a second. Sure.
If you neglect the quadratic term in the velocity, it's like saying no inertia.
Right.
And you mentioned it at some point before, if you do this already in the setup of the free energy, if you kick out kinetic energy, what should be the same, it's not the same.
No, I mean what happens if you kick out inertia from the beginning, then you do it at this level, right?
Yes.
So what you will get is just force balance. Now, if I have force balance, then I mean there's no way that when I do the time derivative here, that the stress appears, right? So what you would have to do maybe, but I've never managed to do this, maybe through something like introducing a Lagrange multiplier, which conserves momentum, you might be able to introduce sigma, so the stress tensor, right, from independently of having really explicitly the kinetic energy and momentum in there.
Well, I mean, having to do it at the end doesn't mean that the variation and all this transformation somehow split the term into two that are then on two different levels, and you can remove one of them and the other not?
Well, I guess what you're referring to is that if you derive the kinetic term, there it is, then you have these two terms. So you have one term which has the momentum, and then you have the one where you get again the mass density changes, right? And this is here.
And this term that you...
This term which basically kicks out.
So I have in the deriving Simpson equations, it's a very similar situation. If you kick out second order terms in the small parameter, in the wave parameter, right in the initial integral, you lose capillarity entirely. If you keep it inside, you actually split them into two, and then one of them is the classical capillarity that you keep, and the other one you kick out after the variation. And it sounds like inconsistent somehow, but it seems to be adding to what you do.
I would say, first of all, inertia is there, we know this. So we have to write down the complete equations first.
Yeah.
Then we know what we should really solve, and then we can look at limits. Right? So there was a time when I was very worried about this. Maybe I just got used to it. I'm much less. So because you somehow have to introduce the mechanics in there, and mechanics you can only get if you talk about momentum. And so you have to talk about momentum with some choice of forces. And the question is how you do it.
Maybe you can introduce friction here.
Friction.
Friction, like a body.
But then I
body
would.
dissipation.
But then I would have to worry about boundaries, right?
No, you see, say if it is, if you are not for a volume, but for a layer.
Yeah, but as I said, but then you have to. But this is then an external force, right?
Yeah.
So this comes in also in the above equation, and then I don't know how to introduce this in the free energy. So
External force. Yeah.
and so let's put it this way. So this is one way that is clean enough for me.
So this is maybe just an additional term.
Yeah, I mean, so that's something one might. So one might use this what is called Rayleigh function, also maybe to extend the energy of the system, and then do the calculation. That's possible. I don't know. People were thinking about this, but for the time being, I would say friction would be for me a boundary condition. So after I derive the volume equations, then I provide the appropriate boundary conditions.
Then, say, it can be simplified from 3D to 2D.
Yeah, sure. Yeah, but this I think is the proper way to do it. If there's a shortcut to it, I don't know. Maybe there is.
I'm sorry, I don't understand this sigma alpha beta you defined last.
This one?
Yeah.
Just a definition. Just because I don't want to write down. So what I want to do is I want to separate this one into a symmetric and into an asymmetric part. And the symmetric part I just do it for sigma alpha beta. So I take the full tensor and subtract the antisymmetric part. Right? And for the antisymmetric part I have a nice expression. And we will see now if all the signs work out correctly. Okay, so let's see what we have. So we have still our integrals. And now we have to replace minus sigma total minus sigma Ericsson by what we have written down there. So this gives us a minus sigma alpha beta times d beta v alpha. And I have to add the antisymmetric part, and the antisymmetric part gives us a minus there, so there should be a plus 1/2 h alpha p beta minus h beta p alpha. And again, I have the d beta v alpha. Then I have a plus everything that comes from my previous terms involving p. So this is a dt plus d beta v alpha. And I have to carry along my argument mu. Right? Okay. So now what I can do is I can go a little bit further and symmetrize this thing here. Since sigma is symmetric, I can also symmetrize this part here. So this is then giving me basically a minus sigma alpha beta v alpha beta, where v alpha beta is nothing but the symmetric part of the velocity gradient tensor. So that's that part. And now comes the thing that is nice, because this one, I'm sorry, yeah, no. So now this one I can write also so that here I let appear only the antisymmetric part of the stress tensor. And this, let us do this, and I will wipe it out immediately afterwards. So what I will do is I will write down this thing again. Then I will change the names of the indices, and then I can just, by inverting the this term, I can factorize it again. So what I will want to do is the following. I will want to write it down in this way. So this is so this 1/2 is because I'm going to write it down twice, so I have to keep it once. So this is h alpha p beta minus h beta p alpha times d beta d alpha plus, and then this gives me, by just inverting and then changing the order, gives me h alpha p beta minus h beta p alpha d alpha b beta. Right, so this is all this term. And what do I get from that? I get an h alpha p beta times d beta v alpha minus d alpha v beta, an effect of 1/2. So this is these two terms, and then I get a minus h beta p alpha from this term, right? And this here is nothing but minus the vorticity, so I can write omega alpha beta as d alpha v beta minus d beta v alpha, and so I can write this term as a plus, and here's like minus h alpha p beta minus h beta p alpha times omega alpha beta. Right. And I forgot the 1 factor of 1/2 that I have to still put in front of that. So here with this I'm not yet finished, because now I can use that this one is antisymmetric, and what I can write down in the end is that this is nothing but h alpha p beta times omega alpha beta. Okay, so that's this term, this one, and then I have a plus h alpha dt plus v beta p alpha plus r. Right, so this is the equation that I've ended up with, and I guess I've probably done somewhere a sign error. No idea where that occurs, but here or there, I mean these signs should be the same. Don't know where I missed that one. That's for you to check. So I guess this global sign is wrong. So let's put a plus in here, right? But this is something you have to check. And so this will then come out as dx sigma alpha beta v alpha beta plus, and now I'm writing this thing here, oops, forgot, plus h alpha d by dt p alpha, and plus r delta mu, where d by dt p alpha is nothing but the convected co-rotational derivative of p. So what is this? d beta p alpha plus omega alpha beta p beta. Right? And so even though in the beginning for the hydrostatic considerations we separated in the spatial degrees of freedom from the autoparameter degrees of freedom, here now we see in these in this derivative they all come in together correctly as they should. So this is basically what I wanted to end up with. This is the expression that identifies clearly the fluxes and forces in this system. And so I have my fluxes. The fluxes, they should be sigma alpha beta. They should be d by dt p alpha, and it's r. And the conjugate forces, they would be v alpha beta, would be h alpha, the molecular field, and delta mu. Right? And basically, as I said in the beginning, I mean, if this were part of the other workshop, everybody would know this. This part here, this is just standard liquid crystal theory. And what we do is we just add this one, basically. Right? Okay. And now we can get the constitutive equation by just doing our linear expansion. What I said is that this is a constant. This I will keep constant. Yes, and now you will see that there are phenomenological constants that are coming in. So they should be constants if you are strictly at the linear level. But then at later times we will take the freedom to introduce further nonlinear dependencies in order to get interesting effects.
Somehow make them up based on probably ideas about.
Well, I mean, yeah. Okay, so if you want, you can say you make them up. On the other hand, we know that at some cases there is really an important dependence of the activity on the amount of motors, for example. And so the amount of motors would be, the motor distributions would be additional fields in here. And you could again do this all in this framework, but these we do add by hand. And then for the reaction rates of the motors, you take the freedom to introduce nonlinearities by hand, those that we think are appropriate and necessary to explain certain phenomena.
So you don't have to disturb this u with d alpha beta t beta. Why people are didn't get it? You have omega.
Yeah, so there's no.
So
I mean, there's this one here, but there's no. I know. Have to ask them. I mean, here there's no reason to. I mean, what you do get. Let me first write down the constitutive relations and then define the final form. So now I do a linear expansion. So this would be the first term, and this would just be Stokes, right? I mean, this is Stokes' equation, basically. Stokes' expression for the stress, and then if you put everything back up again, then you would see that you get the Stokes equation. If I had kept the inertia term, then with this definition I would get Navier-Stokes equation. Right? It's just the usual framework of hydrodynamics. So now what I would like to do, I mean, I have more forces, I have the H and I have the delta mu. I want to couple them. Now, of course, I have to respect Curie's principle. I can only match together things with the same vectorial order. And for this, I exploit that I have a local anisotropy in my system. And so what I will do is we'll have a u1, I guess we divide it by 2, maybe just to be consistent. Doesn't matter. So this is a p beta, but I want to have it symmetric because sigma alpha beta is symmetric. So I put in here plus p beta h alpha. So this would be the coupling to the orientation field. There is another possibility to add it, and that would be plus mu 1 bar. And that would be because I want to be at the want to be consistent. Then I write down the I have to write down the same order of things. So writing here p gamma H gamma times delta alpha beta. So these are all the terms linear in H alpha, in H in our molecular field that are consistent with the symmetries of this term here. And then, and for historical reasons, there's a minus in here. We write down the coupling to delta mu. So first of all, there would be an isotropic term, alpha beta delta mu. But now, due to the anisotropy, I can form further terms. So I have a minus, let's say, zeta p alpha p beta delta mu, and a minus c tilde p gamma, because I want to be at the same order here, right? Delta alpha beta delta mu, right? So that are the terms that are allowed by symmetry to lowest order in the quantities. Then I have to write down an equation for my order parameter field. So first of all, I have the coupling to the molecular field. Then I can now also couple it to the activity here. So I will have a lambda 1 p alpha delta mu, and I think that's it, right? Oh, that's it. And then I can still couple this one to the stresses here, to the velocity gradient tensor. So I can write down now a term that is, what is it, v alpha beta p beta. And now I have to be careful because the prefactors, they are imposed by Onsager, and I will have a minus mu1 here, right? And I will have a minus mu1 bar v beta beta p alpha in here, right? And here you notice the change in sign. This is because of the different behavior and the time reversal of these quantities. So this is why you have the different signs. And then there would be also the equation for R, but I'm not going to consider this, so I don't write them down. So these are now the equations that I wanted to get at. These are the hydrodynamic equations for active polar fluids as we use them. And yeah, that's that part. Are there any questions on this part? Because what I would like to do in the remainder would be a short discussion of topological defects, but with charge plus or minus 1. Yeah, sure. Now you first have a, let's say, lambda delta mu, and then you have the coupling terms, and again, there's no freedom anymore in the coefficients, because the coefficients now they are all fixed by Onsager. And one should also maybe say that first of all there are quite a number of coefficients, right? We have the eta, the nus, and the zetas, and the lambda, and the gamma, and the capital lambda. So there are quite a number of parameters. However, the physics behind many of those parameters is already known from liquid crystal theory, and so the essential new parameters are these zetas here, right? And there you can start if you want with isotropic systems. But what we will often do is to assume that the polarization vector has a constant magnitude, and then basically these terms are the same. So this reduces the number of parameters in the system.
Actually, other non-equilibrium couplings besides you can say the derivative.
Okay, so you could, yeah, but so since we say that for us this is basically spatially constant, there are no derivatives of delta mu appearing.
Okay, it is
Right.
spatially constant. It means that all other processes are constant.
I mean, obviously, you could also go to higher order terms. The problem then is only that the number of phenomenological parameters proliferates. You get more and more of them, and then what do you do with all these things? So either they are measured, then you're in good shape, but usually they aren't. So what we usually prefer to do is then to say, okay, we keep this as the basis, and then we introduce those nonlinearities that we think are the relevant ones.
No, this is what I said. It is still on linear level.
Yeah, okay, yeah, so you can, and also if you think about gradients, the same argument. Okay. Oops. So how do they look like? Well, if I look at the polarization field, then basically what you get is, so this is the center of the defect, you get either things that look like this, and here you might have both orientations, so either the polarization vector is pointing outwards or it's pointing inwards. And so this is a configuration we will call esters. You can have something like this. And again, you might have the things, the polarization vector pointing clockwise or counterclockwise. I'll not write them all down, so you get the idea, I guess. And this is what we call a vortex. And then you might also have a different angle of the polarization vector. I'm not so sure that I will be able to draw this nicely, but this is something we call a spiral. And so such structures are observed in experiments, and I guess this is basically one of the founding experiments of this whole field where these things have been observed, where people purified motors and protein and filaments, and they used a trick to assemble different motors together, and then they had basically an in vitro reconstruction of essential elements of the cytoskeleton. They added the motors, ATP, and the filaments, played some tricks, and then what they observed were indeed structures like esters and vortices and spirals, and so they were right at the beginning of all this field. And so the question is, can we say something about these structures? And so what we are going to do is we're going to consider an incompressible fluid. We will assume that the order parameter is of constant magnitude 1. We will use polar coordinates. So if I have, here's my coordinate theta. If I look at the polarization vector P at this place, then what I can do, since it has unit length, I can basically describe the position here by an angle psi. So I will have this PR is just cosine psi, P theta is sine psi. If I then look at the molecular field, OH, then I obviously also have the components HR and H theta, but it turns out to be convenient to look at components projected on the direction of P locally and perpendicular to it. So what I have is basically, and just to get the signs right again, I should better look it up. So this is H R cosine psi plus H theta sine psi, and H perpendicular is then HR sine psi minus H theta cosine psi, right? So it's now you describe basically the molecular field vector in terms of these components H parallel and H perpendicular. And so what H parallel does, it basically fixes the length of the order parameter. So what we are going to assume is that this is a Lagrange parameter, a Lagrange multiplier, and it fixes the length of the polarization vector, and this one is then really the component perpendicular to the polarization vector, so this one is turning it, and so this one can be obtained by deriving our free energy with respect to psi. More calculation that you have to do in order to show that. Then I have to specify now the part of the free energy that is due to the polarization, and I will use the standard lambda de Genève formula or expression. So this will be k by 2 1 over r d by dr cosine psi squared plus, and I will basically assume that the band energy and the band modulus and display modulus are the same. So I will just have a one constant approximation d by dr sine psi squared. Right, so these are the expressions that I'm going to use, and from that I can get easily the expression for H perp. I'm not going to do this explicitly, but this is just the Laplacian of psi. Right. So that's easy. And now you can plug in all these expressions into the equations that I've shown you before, and then you will get an equation for psi. That is dt psi. This is now a rather horrible equation, but I'm going to write it down anyways. That's 1 over gamma plus 1 minus u1 cosine psi, no, 2 cosine 2 psi squared divided by 4 eta plus gamma u1 squared sine squared 2 psi. That's the first term. All this is proportional to k, and then we have here our Laplacian, and we then have a term. So this is basically the term that is proportional to H perpendicular, and so the only thing that we have to look at is really the evaluation of the order parameter P, that is psi, but we have also the coupling from the activity, and that is 1 minus u1 cosine 2 psi times sinus 2 psi, and this divided by 4 eta plus u1 squared gamma sinus squared 2 psi times zeta let's call it hat delta mu, and theta hat would be theta plus gamma plus lambda 1. So this is really the activity. It's how the activity plays on the autoparameter directly, and this is through the stresses that are generated. Okay, so what do we get from this equation? So first of all, we get steady state solutions. And there are some easy ones, namely when psi is a constant. And these are basically the only ones I'm going to consider. So you see if psi is a constant and this term drops out. So for a passive system where delta mu is equal to 0, defects with any orientation of the order parameter are fine. This is basically due to the fact that we have set the two elastic constants, the one for the splay modulus and for the bending modulus, equal to each other. So it doesn't matter if you bend or splay the system. So this is why you get all angles with no difference. But if you have the activity inside, then things are a little bit more interesting, because this restricts us to certain values of psi naught. So I can either make the sine of 2 psi equal to 0. So this gives me that psi naught should be either 0, should be pi half, pi, or 3 pi divided by 2. So these are just our esters and vortices with the different orientations of the polarization vector. But then I also have that I can, under some circumstances, make this term equal to 0. And that is if, well, let's say 1 over the modulus of mu1 is larger than 0. True. No, it's just the opposite, right? If the modulus of mu1 is larger than 0 or equal, then I have another solution that is determined by 1 is equal to mu1 cosine 2. So I have, in the active state, I have the esters and vortices like in the passive state, and if my parameter mu1 is large enough in modulus, then I can have also a spiral solution, or two spiral solutions pointing in one and the other direction. And when we have a spiral, then things are interesting insofar as the spirals are moving. This is still what I'd like to do, and that is so. Oops. What you can show, this I'm not going to do, is that the theta r component of the velocity gradient tensor can be written basically as some constant that depends on the value of psi naught times delta mu. Now, where I should maybe say that for psi naught equal to 0, or for pi half, or for any of these values, is 0. But for any other value, so when you have a slight inclination of your polarization field, then you have gradients, and then this can be solved and gives you a velocity which is just a psi naught times r, and then the logarithm of L divided by of r divided by capital R, where capital R would be the boundary of our system, and the boundary of our system would be such that there is no motion at r, so v of theta should be 0, and at the same time the boundary condition on the polarization vector should be such that it agrees with psi naught, right? So in this way I can have my polarization vector pointing this way, for example, and then what will happen is that this whole thing is going to turn. And this is what you can see, for example, nicely in experiments done in just a few meters from here in Ray Goldstein's group, where they have bacteria confined in petri dishes or in chambers of circular diameter, and you see that they are nicely swirling around. So what you can then also do is you can study the stability of these states. So if here I have delta mu, so let's put it here equal to 0. At zero activity, well, let's put on this axis delta k, where this is just the difference between the, what do I have, bend and splay modulus. Yes? Oh, you have to plug everything into the equations, and then you go work your way through, and after 2 or 3 pages you get the A. I don't want to, I mean, this one is a little bit tedious to get.
That's the most important part.
We can go through the calculations together if you want. Yeah, I'm sorry, but this would now, especially I'm getting to be tired, so I guess I would commit errors in the calculation now. So, but basically what you do is you use the constitutive equations that we had before. From this you get lib psi, right? Then you have to express the tensor for the velocity gradients in terms of this solution, right? So we saw that it depended on sigma, theta, r, and other contributions. Then you have to collect all the terms, and you will see what ends up is something that's proportional to delta mu and a prefactor that is not very nice. But it doesn't have any, I mean, this particular value doesn't play a big role now. I mean, it's just that it's different from 0 if psi naught is neither, so if the polarization vector is neither orthoradial or radial. That's the only thing I think that is really important here. And the nice thing is then that this really turns. You can look at a slightly simpler situation if you want, but I will not do this today anymore. So what you can do is you can look at a system between 2 plates, and you look at a state where initially the polarization vector is pointing parallel to the walls of the thing. What you then can see is that, so initially you would say this system is at rest, nothing will happen. And then what you can look at fluctuations in the or deviations of the polarization vector from the state, and you will see that as soon as the so in an impassive system they would just go back to the state, right? Because of the system wants the polarization to have equal orientation everywhere. But if activity is large enough, what you will see is that then spontaneously you can break this, let's say, translation symmetry in this direction, and you will have a situation where you get such a state. So now you have gradients in the polarization vector. What you will then see is that you will generate spontaneously a flux in the system. And so this is only due to the activity in the system. Get an instability of this parallel alignment, and oops, will turn out, and then you will get a flow in the system, because gradients in the polarization vector, they couple to our gradient field for the velocities, and this will get you things moving. And this is what people call also sometimes a non-equilibrium or active Fredericks transition. Because it's similar to an effect that you know from liquid crystals, where you have a, let's say, magnetic liquid crystal, and you apply a magnetic field from the outside. If this one is strong enough, then you might get also here an instability and generate a flow. Okay, let's come back to the spirals, or to these topological point effects. So if the system is passive, then what we will have is Well, since here the bend costs more energy than display, you will have esters, whereas here you will have vortices, because the display costs more than to bend the system. And then what you will see is that you get an instability, something like this, so that here outside, well, you only have spirals, and here you have these turning solutions. But you also see that if the system is below the critical activity, then these vortices and esters, they are indeed stable, and they are obviously not moving, and there's no flux associated with these states. Okay, so and I think this is where I want to end. What we are looking now at is, in fact, what happens if you have two spirals, two defects of this kind. They will interact and they will move. And the question is, how will they move? This is what we're doing right now. Okay, with this, thank you.
Transitions to the other defects become unstable, or if they are in overlap?
I don't know. So I don't know. I think it's. I assume that they are second order, supercritical bifurcation. But
so you take a solution and check the stability of
yeah, so we did not do that. No.
Suppose your boundary conditions are favor a wrong defect. What will be?
Yeah, okay, so I've always looked only at situations where this one is compatible with the defect. So there's plenty of things that one can look at.
Well, it might be like the way they can change in between.
Okay, so, but then I guess one should have some energy that...
It may have some transition.
Yeah. No, nothing says that you have to be in the strong anchoring regime. Right? I mean, in the simplest case, you would just say it's free to turn. But in general, I guess there should be some interaction between the director and the boundary, and then one would have to account for this to the boundary conditions. Yeah, but as I said, I mean, there are plenty of things that one can and should do with these defects.
Have you looked at them in, let's say, in films? I mean, between plates? Or
Experimentally, you mean?
yeah.
Well, between plates, I'm not so sure anybody has looked at it. So,
Like it's
like,
not 2D, right?
I mean, in Ray's experiments, they have always one free surface, as far as I know.
It's like infinitely extended.
Well, no. So, I mean, there are also these large films, right, studied by also Ray and Ivar Aronson and other people. But there are also experiments where they confine them to circular domains, and they see the spontaneous onset of rotary motion. We knew that this would happen, but
Yes, but it's just
nice
like
that they
the
see it also.
domain of a film, right, of constant height. For the droplet. Yes.
I mean, this is all 2D, right? And we don't really care about the boundaries top. But I mean, many series.
The flow will be a bit different.
Yeah, so what we have looked at is what happens if you have friction with the substrate. It changes a little bit the system, but not too much. Well, it's more quantitative than qualitative. So here, if you want, is the free suspended film. And then the experiments on cytoskeletal elements, they are also done with a free upper surface. And there, I mean, one of the main achievements of this experiment was to get the filaments and motors not too stuck to the substrate. And they spent, François and Delec spent, I mean, lots of time to get clean glass surfaces.
But they would settle somewhere?
They will settle, they would just stick, and then what you have is what they call a motility assay. So you have motors sitting on a for example, motor sitting on the glass, and on top you have these filaments and they move. You could have the inverse, but this is not what they wanted to study. They wanted to see only the effects of relative motion induced by the motors. Okay.